One moment. Okay, so today I think we should finally kind of get back to where everyone's kind of on the same page. We'll talk about differential equations for a little bit, and then we'll talk about improper integrals. Which hopefully sounds like content, at least the improper integrals, that is familiar to both classes. Oof. Oops. One more. Sorry, one more second. Come on. There's one thing I'm looking for here. Okay, so differential equations. We do a very light treatment of differential equations in this class. We're just going to talk about one type of differential equation. And really, the truth is when you take 22B, that's when you'll actually really learn about like differential equations. But very broadly, a differential equation is an equation that involves a function and one or more of its derivatives. So probably the one we care about the most is this one. dy dt equals some constant times y. If we think of y or y of t as our population at time t, and really this population can be like the number of people or the number of cells, or if we're talking about radioactive decay, it can be the amount of radioactive material. It's really more the amount of stuff you have at time t. Well, this differential equation can be solved by a process known as separation of variables, where you bring all of the y things or function things to one side and all of the variable things or t things to the other side. Specifically, you want your differential dy or dt to not be in the bottom. You want it to be in the top. So I'm going to bring the y over here and say 1 over y times dy dt equals k, and then essentially multiply both sides by dt and say that 1 over y times dy is equal to k times dt. And then we're going to, not surprisingly, anti-differentiate both sides. So solving this, we get, yeah, we'll say that, the natural log of the absolute value of y, although most of the time you can really just ignore that absolute value, and I'll talk about y in a second here, equals the antiderivative of a constant is that constant times your variable plus another constant. So now we're going to solve for y. So I'm going to write both sides as e to the stuff, so e to the natural log of the absolute value of y equals e to the kt plus c. And specifically for this setup, whenever you have this kind of thing happen, we do a couple things. First of all, e to the natural log of absolute value of y is just the absolute value of y. And it's going to equal, I'm going to rewrite this right-hand side as e to the kt times e to the c. I'm going to rewrite it as e to the c times e to the kt. And then since the absolute value of y is equal to all that stuff, y either has to be the positive of all that stuff or the negative of all that stuff. And then what we typically do is you say, hey, this plus or minus e to a constant is still just a constant. Whether it's negative or positive, it's some constant. So we're just going to call it something else, usually A or C naught or whatever letter people like to choose. It really doesn't matter, but people usually call it capital A and say we have y equal to A e to the kt or C e to the kt, or, it doesn't really matter. But the point is, this function y of t equal to a e to the kt, where a and k are both constants, is a solution to this differential equation. You can even check it, right? If you find the derivative, dy dt, the derivative of a e to the kt is, well, the a hangs out. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. But look, that a e to the kt is exactly your y of t, so it's exactly equal to k times y of t. So this really indeed is a solution to this differential equation. And again, all that means is we found the function that does the thing. Most of the content in solving differential equations or in the differential equation section is solving via separation of variables. However, there's one other kind of thing people like to ask sometimes. So we'll come back to this example in a bit, but I will point out this one's super important because this is the model for exponential growth, y equals a e to the kt, and it comes about when your rate of growth, dy dt, is proportional to or a multiple of population size. So when the rate of growth is proportional to the population size, the growth can be modeled by, or I should say the population size can be modeled by exponential growth. We have an exponential model. That always happens. So yeah. Let's kind of take a quick journey aside here and then we'll come back to this. So sometimes people like to ask questions like the following. Where'd you go here? Sorry, I've got all sorts of things here I'm looking at. Yeah. So most of our differential equations, actually, pause. Any differential equation you're asked to solve in this class will be separable, meaning you can get all the y's on one side and all the t's or x's or whatever your input variable is on the other side, and then integrate both sides and solve for y. It's usually not too bad. The other thing, though, sometimes we like to do is ask to show that, for example, what have I got here? Y equal to x e to the x cubed plus c e to the x cubed is a solution to the differential equation y prime minus 3x squared y equals e to the x cubed. Most of the time, this involves taking your proposed solution and then looking at your differential equation and say, okay, well, my differential equation has the function y and the derivative of y. So I need to find both those things to then substitute in. So we're going to find y prime by just differentiating. So y prime is going to equal, okay, I got to use the product rule here. It's going to be 1 times e to the x cubed plus x times e to the x cubed times the derivative of x cubed plus the derivative of c e to the x cubed is c e to the x cubed times the derivative of x cubed. Pretty gross looking. So then what I'm going to do is I'm going to substitute all of this in for y prime and all of this in for y, and then hopefully it works. It should if they said it's a solution. If they say show it's a solution, it should work. If they say check to see whether or not it's a solution, then it might not end up equaling it, and you're like, no, it's not a solution. So here we're going to plug in all of that. Yeah, it's going to be kind of gross. So I'm going to have my y prime, which is e to the x cubed plus, I'm going to simplify this. That's a 3x squared times an x, which is a 3x cubed e to the x cubed plus a c times e to the x cubed times 3x squared minus, so that's all of y prime right there, 3x squared times my y, which is x e to the x cubed plus c e to the x cubed. And here's what I'm not going to do. I'm not going to say that's equal to e to the x cubed. I want it to be, but I don't just get to say it is. So I'm actually just going to simplify the left-hand side of this until I get to where I hope I end up at. Bless you. So distributing the minus 3x squared, we're going to get e to the x cubed plus 3x cubed, e to the x cubed plus c e to the x cubed. Oh my God, 3x squared minus 3x squared times x is 3x cubed e to the x cubed, and 3x squared times c is c times e to the x cubed times 3x squared. And let's see, the minus c e to the x cubed 3x squared cancels with the plus one. Cool. And this cancels with that. So we end up getting e to the x cubed, which is what we want the other side to be equal to. So it works. So that shows that y equal to x e to the x cubed plus c e to the x cubed is a solution to this differential equation. It's a little tedious, but it's also totally fine. So when we see something like this, we want to check, I should say, we want to look at our differential equation and kind of identify all of the functions and derivatives that are present and then find them all and then plug them back in to see if it actually solves the thing. So let's look at maybe two more examples. But here's a more interesting example. So let's ask the question, is y equal to sine of 4t a solution to d squared y dt squared? Oh, I have to remember how this goes. Sure, that's going to be that. Plus 16 times y equals 0. You guys do it. Take the second derivative, jam it in right there, do 16 times your function right there, and see if it's equal to 0. This question. All right, let's take a look. So my first derivative, not that I need it, but I need it because the second derivative is going to be cosine of 4t times 4. And my second derivative is going to be negative sine of 4t times 4 times another 4. So it looks like my d squared y dt squared is going to be negative 16 sine of 4t plus 16 times y, which is sine of 4t. And yep, those things sure do add up to 0. So it works. That is a solution to this differential equation. It's not the only solution. Cosine of 4t would also be a solution. Kind of neat. I think we have two more to look at before we go back to those stuff. So yeah. This one's a little bit different. So is x squared plus y squared equal to c times y a solution to y prime equal to 2xy over x squared minus y squared. This one's a little bit funkier. For one, we don't have y explicitly in terms of x. So when you see this kind of thing, if you see this kind of thing, the first step should just be to take the thing we think is a solution. So here's our proposed solution. And since we can't explicitly solve for y, or we shouldn't really, because you probably could if you really, really wanted to, we're going to just differentiate both sides implicitly. So we're going to differentiate implicitly, meaning y is a function of x. So the derivative of x squared is 2x. The derivative of y squared is 2y times the derivative of y. And the derivative of c times y is also, well, not also, is c times the derivative of y. And then what I'm going to do is I'm going to try to essentially make this look like that, which feels kind of weird, but it's all I got. So first, I guess I should try to isolate y prime. So I'm going to say, yeah, 2x equals cy prime minus 2y times y prime. And I'm going to factor out a y prime. So I'm going to say that 2x is equal to y prime times c minus 2y. I'm going to divide by that. So then I'm going to get that 2x divided by c minus 2y is equal to y prime. Not quite there, right? Y prime is 2xy over x squared minus y squared. So there's a couple ways to go about this next step. What I would try to do is I would really like the top to have a y in it. So it's certainly not allowed to multiply the top and bottom by y. So what we're going to say here is now y prime is equal to 2xy over c times y minus 2y times y, or 2y squared. But now, what's c times y equal to? These ones are often tricky because you often have to use the original equation to kind of sub back in. Oh, c times y is equal to x squared plus y squared. So this ends up being y prime equals 2xy over x squared plus y squared minus 2y squared. And then y squared minus 2y squared is negative y squared. So we get 2xy over x squared minus y squared, and that checks out. It's kind of weird. I won't lie. It's a little bit like you have to play with it to make it work. And it's definitely less easy when we don't have y explicitly as a function of x. But it's still usually pretty doable. Yeah. Yeah, it's a little weird. So again, for these kind of problems, they're usually just telling you what the solution is, and then you're checking to see if it actually is a solution. Or usually it's a checking to see that it is a solution. Usually they say, this thing is a solution, check to make sure. Because otherwise it feels like you're kind of spinning your wheels if they're like, is it or is it not a solution? I don't know. We're going to find out. Yeah, I do. I think. I know I printed it. I have it over here. Somewhere in here it is. Yeah, there we go. Cool. Thanks, really. Thanks. All right, so let's see if there's a question here. Could you go over on how I added y to the numerator? Definitely. So from here to here, what I saw was, well, I'm trying to get to here. I see that I have a 2x in the numerator. I want a 2x times y in the numerator. So I really just said, well, I can't really change this thing, right? I'm not allowed to just put a y on top, but I can multiply the whole equation by y over y. So that's what I actually did in that step, was I multiplied by y over y. So now the numerator is 2x times y, and the denominator is c times y minus 2y times y, or 2y squared. And then after that, we use the fact that cxy was equal to x squared plus y squared to replace this cy is equal to x squared plus y squared, to replace the cy here with the x squared plus y squared right there. And then we simplified to get, oh yeah, it is. Okay. So let's see. Let me look here real quick. So um the ones we solve are usually a little bit more interesting to work with. So let's look at something like this. Let's say we have the differential equation dy dx equal to e to the 2x minus y. And we want to solve the differential equation. Sometimes we'll be given an initial condition as well. And if you're given, which you're not in this problem, but if you are given an initial condition, we then have to additionally solve for whatever constants show up. So if I'm going to solve this differential equation, well, I know I have to be able to separate the variables. There's no choice, right? In this class, the only method we know is separation of variables. In other classes later on, you'll learn about other methods like first order linear differential equations and all kinds of fun stuff. But for now, we're just trying to separate things. So we really want to write the thing that dy dx is equal to as a function of x times a function of y. So I'm going to write this as dy dx equal to e to the 2x times e to the negative y. And then I can separate things without too much issue. I can bring my y's to the left. So I'm going to have dy over e to the negative y equal to e to the 2x times dx. And before I integrate both sides, it really doesn't make sense to leave that e to the negative y in the denominator. I'd be much better served by writing it as e to the y times dy equal to e to the 2x times dx. So then we can integrate both sides relatively easily. So we get e to the y on the left and e to the 2x divided by 2 plus c on the right. Now, why do we put the plus c on the right instead of on the left? Or even on both sides? Well, typically with these problems, we're trying to solve for y. So usually you want to put as little stuff on the y side as possible. But if you wanted to, you could have said plus c1 on the left, plus c2 on the right, and then subtracted the c1 over to the other side to say that e to the y is equal to 1/2 e to the 2x plus c, where that c is c2 minus c1. So that's why you're just allowed to put the c on one side, because if you put it on both sides, you can just bring it over to the other side. And then we solve for y if we can. We can't always solve for y. Sometimes you get something really gross on one side, like if you had like natural log of y plus y squared, there's no way you're solving for y there. But if you can solve for y, you should. So taking the natural log of both sides, we get natural log of e to the y equal to the natural log of 1/2 e to the 2x plus c. And unfortunately, there isn't anything else we can do with this. We're stuck with that. So our solution here is just y equals natural log of 1/2 e to the 2x plus c. Our general solution, because we didn't have an initial condition. Let's look at one or two more examples, and then we'll talk about improper integrals, because that's a lot more interesting. This stuff isn't not interesting. It's just we don't really have enough of the tools to really solve the more interesting problems here. So another example could be something like the following. dy dt is equal to y times natural log of y divided by 1 plus t squared. And we're given the initial condition, y of 0 is equal to e squared. Whoops, can't quite see that. Apologies. Let me scooch this up a little bit. That'll be easier for me. Okay, so same thing as always. We'll start by separating the variables. So I should also mention, if you're starting with dy dx or dy dt all by itself and the other stuff on the other side, the only things we're really allowed to do are multiply and divide. We can't add stuff to dy dx or subtract stuff from dy dx. It doesn't really work that way. if we want the variable separated, the y is on the left and the x is on the right, or t is on the right, we have to have your function of y times dy and your function of x times dx so that we can then have a normal integral looking thing. So we're going to have on the left-hand side, I'm going to divide by y natural log of y. So I get 1 over y natural log of y dy equal to 1 over 1 plus t squared dt. We've separated things, so now we can integrate. One of these sides is straightforward. One of them is not. The right-hand side is just going to be the arc tangent of t plus c. The left-hand side, we have to do a u sub. The left-hand side, we're going to let u equal the natural log of y. Our du is 1 over y dy. So this ends up becoming the integral of 1 over u du, which is then going to be the natural log of the absolute value of u. And then that's going to be the natural log of the absolute value of the natural log of y. So here's our solution. It's the natural log of the absolute value of the natural log of y equal to the arc tangent of t plus c. And a good question to ask yourself is, when should I try to find my c value if it's an initial condition problem? Well, with practice, it becomes a little more clear when is kind of the best moment. Now is not the moment, because if I find c right now, I'm then going to have to kind of do all the things I do to both sides to it. Well, that's probably kind of true here anyway. Well, let's see. So I'm going to undo one of these natural logs by saying e on both sides. So e to the that equals e to the that. So I'm going to have just the absolute value of natural log of y equal to e to the arc tangent of t times e to the c. Right? Or I could have a plus c up there, but that's really just e to the arc tangent of t times e to the c, which I really would just rather call a. So I'm going to say that my natural log of y, dropping the absolute value, because I'm going to get the plus or minus in that e to c there, is equal to a times e to the arc tangent of t. Is now a good moment? Maybe. Probably. I think so. Yeah, let's do it. So I plug in y equal to e squared. The natural log of e squared is equal to a times e to the arctangent of 0 is 0. Cool. A equals 2. But then we're not quite done. I'm almost out of space here. That's unfortunate. So then we still have the natural log of y equal to 2e to the arctangent of t. And now this is where things are going to get a little bit gross. If I do e to both sides again, I'm going to get y equal to e to the 2 times e to the arctangent of t. Yeah, it's kind of awful. That's our solution. And we found the constant a or c or whatever you want to call it. Now, if I hadn't found a right there, I would have still had an a right here. So if let's pretend like, let's go back and say I hadn't done that. And let's say we had said that we had that e to the natural log of y was equal to e to the a times e to the arctangent of 2. Gross. So I end up getting y equal e to the a times arc, oh my gosh, a times e to the arctangent of t. Sorry, I think I said 2 before, apologies. Arctangent of t. So then I can plug in my initial condition and get y equal to e squared, apologies. And that's equal to e to the a times e to the arctangent of 0. Better? Probably not. But also still ends up with the same result, because arctangent of 0 is 0, e to the 0 is 1, and a times 1 is a. So you end up getting just e to the a, which means a has to equal 2. So we still get a equal to 2 that way. but it probably would have been less nice if we'd gone right from the beginning and said, okay, right here, if I plug in, right here, if I plug in y equals e squared and t equals 0, then you have to kind of do all the math to that constant along the whole way. So it can be a little bit gross that way. All right. Should we do another one? The answer can be no. I don't want to do another one. We can do more if we feel like we need to at the end of class or another time. So most of the time, solving differential equations, well, in this class, solving differential equations is always via separation of variables. You're always putting all the y's on one side, all the x's or t's or whatever inputs are on the other side, and then integrating both sides, solving for y as a function of t or x or whatever. Let's see what this person is asking here. Could we maybe do one in an application problem? Yeah, question. So typically what I'm saying here is e to a constant is just a constant. And I like to call it capital A. Some people just call it C again. I like to call it a different thing so I can kind of notice that I've done a thing from one thing to another. But yeah, that's what's going on there. Sure, an application problem. Let me look here. So I'll point out most of the application type problems specifically are related to exponential growth and decay. So here's an example from the textbook. Yeah. Oops, not you. Yeah, let's see which example am I going to pick. That seems reasonable. Sure. So this is number 27 from section 8.8. No, sorry, 7.2. Apologies. So the intensity L of x of light x feet beneath the surface of the ocean satisfies the differential equation dl dx equals negative k times L, where L is the light intensity and k is some constant. As a diver, you know from experience that diving to 18 feet cuts the intensity in half. So when x is equal to 18 feet, the intensity is cut in half. We're going to do more with that in a second. You cannot work without artificial light when the intensity falls below 1/10. So if the intensity falls below 1/10 of the surface value, we need artificial light. So how deep can we dive and not need an artificial light? Now, I'll point something out here. Whenever you're given the situation where the derivative is a multiple of your function, we know the solution is the exponential growth model, right? Here we're just saying the rate of growth of our light intensity or the rate of decay of our light intensity is proportional to how much light intensity there is. And that kind of situation always means you get exponential growth or decay. We could also solve the system though, right? We could totally separate variables and say 1 over L dl equals negative k times dx and integrate both sides. Okay, I'm going to ignore the absolute value when I integrate 1 over L. So I'm just going to say that leads me to the natural log of L equal to negative kx plus c. And then if we solve for L, e to the natural log of L equals e to the all this stuff. So we have L as a function of x equal to e to the negative kx times e to the c. I'm going to call that capital A. So L of x equals a e to the negative kx. Personally, I don't think you need that negative sign there. People introduce it to remind you that you have decay instead of growth, but it's actually totally unnecessary. If you didn't write it, you just get k being a negative number instead of whereas here, we're going to get that negative k is a negative number. Same thing, really. So it's really, really unnecessary, but people like to do it, so whatever. And it's how the book wrote the problem. All right, so this is our model for the light intensity at depth x. There is an extra challenge with this problem in that they didn't tell us the light intensity anywhere. Right? We have no actual values. We just know that if we go to a depth of 18, it's going to cut the initial amount in half. So there's a couple different ways you could deal with this. One way is to just say, okay, well, we know the light intensity at the depth of 0 is some surface value. You can even say it's, I don't know, I can call it, what would I pick? I'd call it like S naught for the light intensity at the depth of 0, and S is for surface. I'm just making up a thing though, really. And then we know from experience diving that if we go to a depth of 18 feet, the surface intensity, the surface light intensity should be cut in half. So it's 1/2 times S naught. This is going to allow us to find that constant K, because we need to find that to be able to answer the final question. This A though, that A really is our S naught. So I could have just called it A, in fact. You can do it this way. That's not what I prefer to do. I like to just make up numbers, to be really honest. I like to say, cool, at the surface with a depth of 0, the light intensity is 100% of what you get. So just call it 100. Totally fine. And then 18 feet deep, the light intensity is half of 100%. It is totally, totally, totally fine to make up numbers like this. It also works totally fine when you're doing like radioactive decay, and they say some unknown amount of stuff decays by 30%. You can say, cool, I'm starting out with 100 grams or 100 pounds or 100%, and then just use nice numbers. Either way, you get the same result though. So then we're going to say, all right, well, I know that if I then actually plug in these numbers, well, if my L of x model is a e to the negative kx, it's an x, believe it or not, then if I plug in 0 for x, it should be equal to a e to the k times 0, which is going to be equal 100, or S naught. I'll do both. And then that means that my a times 1 is 100, or S naught. So now my new model, my refined model, is that L of x equals 100 e to the negative kx, or if you prefer this other way, S naught e to the negative kx. I'll point out, by the way, we've totally done this before, or you have at least done this in 21A, right? This is just exponential growth and decay, where you're given a couple data points, you plug them in, you solve for your constant in front, you solve for your constant up top, and then you answer the question by plugging in the appropriate thing. So this is not like a new thing, it just got more context to it now. So then we're going to use our other data point, which is that L of 18 equals 50. So L of 18 equals 100 e to the negative k times 18, and we're going to say that's equal to 50. Or if you like this model, L of 18 equals S naught e to the negative k times 18 equals 1/2 the initial amount. And here's where things converge to the same spot. Either way you solve this, you're going to get e to the negative 18k equals 50 over 100 is 1/2, or 1/2 S naught divided by S naught is 1/2. And so we end up getting that negative 18k equals the natural log of 1/2, and k is equal to the natural log of 1/2 over negative 18, which is a positive number. Natural log of 1/2 is a negative number, and a negative over a negative is a positive. So we still do get a negative number multiplied by x in our model because it's a negative k, and k is positive. All right, so we've got our full-fledged model now, using all the paper in the world here. I guess I can write it here. So our full-fledged model is going to be L of x equal to 100 e to the negative k. I really don't want to write negative natural log of 1/2 over negative 18. Let's just write natural log of 1/2 over 18. That's your negative k times x. Or s naught if you prefer that there. And then to answer the final question, we're going to set this equal to 1/10 of the original amount, because that's how deep we can dive before the light is too low to be able to not use artificial light. So we're going to set L of x equal to 100 e to the natural log of 1/2 over 18 times x equal to 1/10 of 100, which is 10. Or this could be s naught, and this could be 1/10 of s naught. And either way, when you go to the next step and try to solve for x, you're going to get 1/10 on the right-hand side of this equation. Because 10 over 100 is 1/10, and 1/10 s naught divided by s naught is also 1/10. So either way, it works out the same way. So finally, so the point there is that you really don't need to know what the surface level value is. So solving for x, we get e to the natural log of 1/2 over 18 times x equal to 1/10. We take the natural log of both sides. We get natural log of 1/2 over 18 on the left times x equals natural log of 1/10 on the right. When you multiply both sides by 18, and we divide both sides by natural log of 1/2. And if we don't have a calculator, we leave our answer like that. If you do have a calculator, you can actually calculate it and get approximately, let's see. Yeah. We get approximately, that's pretty deep, 59.79 feet. I mean, it feels deep to me. I don't know. That might not be really deep in the world of diving. I'm not a diver. I don't know anything about that, but it feels like it could be a lot more deep than I would be comfortable diving. So, but like that's probably more like 5 feet. Not a confident swimmer. All right. So enough of that. Let's move on. Let's talk about improper integrals, which hopefully both classes are talking about or have talked about or are going to talk about soon. So what makes an integral improper? Well, there's two ways you can be improper. The way we typically start off by talking about is integrals that have a limit of integration that is either infinity or negative infinity. So this is kind of the classic first example of an improper integral. The integral from 1 to infinity of 1 over x dx. So the idea here is that we're looking at all of the area under the curve 1 over x starting at x equal to 1. So we're trying to figure out what that's going to be. Well, whenever we have improper integrals, we are required to use limits. So what we're actually going to do is, instead of looking at that, we're going to say, well, let's say we're going to look at this instead. We're going to go from 1 to some, usually we use b for an upper limit and a for a lower, although you can use any letter you haven't already used. And the idea here is that we're going to find the area under this curve from 1 to b, which is some finite amount of area. So I'm going to find the integral from 1 to b of 1 over x, which we can definitely do. We're going to integrate 1 over x. We're going to get the natural log of the absolute value of x, evaluated from 1 to b. And then we're going to get the natural log of the I don't really need the absolute value of b because the b I've drawn is positive. B has to be larger than 1 here. Minus the natural log of 1, which is just equal to the natural log of b. So that area under that curve is equal to the natural log of b. This area under the curve is the limit of this area as b goes to infinity. So what we would really end up writing here is that the integral from 1 to infinity of 1 over x dx is equal to the limit as b goes to infinity of the integral from 1 to b of 1 over x. We do all this work. We end up getting the limit as b goes to infinity of the natural log of b. And then as b goes to infinity, what happens to the natural log of b? Well, it's really, really slow, but it keeps on increasing and increasing and getting bigger and bigger forever and ever and ever. This limit is infinite. The amount of area under that curve is infinite. So we would say that this improper integral is divergent. So this integral diverges or is divergent. If the limit of the integral is not equal to a finite number, or in other words, if the limit does not exist, infinity being one of those things that doesn't exist, we say the integral diverges. Yeah.
Can you explain how you got a limit from just where you got?
Sure. So let me re-explain with a new example because it will explain it. So the whole idea here is that, well, no, I'll say the words here. So the idea is that I'm finding this area here by looking at this area here and then letting b go to infinity. So that's why I'm using a limit there because the problem is technically, even though people do it all the time, you really shouldn't just plug in infinity because it can be kind of dicey to work with. That's why we're supposed to use a limit every time we have an improper integral, even though sometimes people don't do it that way. You're technically supposed to. So on an exam for sure, if you see an improper integral where one of your limits of integration is infinity, or the other thing we'll talk about in like 10 minutes, you have to use a limit to be properly correct. So let me show you another example. Then let me show you another example kind of in a more typical way of doing it. So let's look at the integral from 1 to infinity of 1 over x cubed, which is slightly less typical. Usually 1 over x squared is the next example people do, but I'll change it up. So similar idea. We're going from 1 to infinity, and we're trying to find how much area is under that curve. So the first thing we're going to do, actually, when we see that the integral is improper, is we're going to rewrite this as the integral from 1 to, usually b is the choice for an upper limit. But again, sometimes people use z or t, but usually it's b for an upper limit, a for a lower limit. I'm actually also going to rewrite my integrand as x to the negative third dx. But it's not just that, it's the limit as b approaches infinity of that. So really it's the same, right? Instead of going from 1 to infinity, we're going from 1 to b, and then we're letting b go to infinity. So typically, when you see an integral that's improper, whatever limit of integration is problematic, we replace it with a b or an a, and then say the limit as b or a approaches that number or that infinity. And then we just kind of carry on. We kind of ignore this limit out front until the very end. So it's the limit as b goes to infinity. I'm going to integrate this. I'm going to get x to the negative 2 over negative 2, evaluated from 1 to b. Then we're going to plug in our limits of integration, which unfortunately have the same name as a limit. Right? Your limits of integration and the limit as b goes to infinity are different things, but they both are called a limit of some sort. So we still have the limit as b goes to infinity. Now, I do think it doesn't serve us very well to write this as b to the negative 2 over negative 2 minus 1 to the negative 2 over negative 2. I think it would be much, much better to write that b to the negative 2 in the bottom as b squared. So I'd much rather write this as the limit as b goes to infinity of 1 over negative 2b squared minus a minus is plus, oh wait, 1 to the any power is 1 over 2. And now we can see that as b gets really, really, really large, 1 over negative 2 times b squared is going to get really, really small. The limit of that's 0. So you end up getting 0 plus a half, which is 1/2. So we would say that the integral from 1 to infinity of 1 over x cubed dx converges, and it converges to the value 1/2. Or you could just say it's equal to 1/2, and everyone knows you mean it converges to 1/2. Those mean the same thing, just one is wordier than the other. So someone asks, what if we had infinity as a lower bound? And I'll say we can't have infinity as a lower bound because infinity is like the biggest thing, but we could have negative infinity as a lower bound. Let's take a look at that. Let's say we had the integral from negative infinity to 0 of, sure, x e to the x dx. Yeah, that's be fine. Okay. All right. So infinity is always a problem, whether it's positive or negative. Always, 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 you have to view infinity as problem child. So we're immediately going to say, great, I'm going to replace that negative infinity with an a because it's in the lower bound instead of in the upper. And then I do need the limit out front as a approaches negative infinity. Now, the first two examples we did were very, very straightforward to anti-differentiate those functions. We just did it. Here, if my process is any more complicated than just I can do it right away, I like to do the indefinite integral off to the side so I don't have to carry all the machinery of the limit and limits of integration with the process. So let's just do this integral off to the side, which is going to require integration by parts. Our u is equal to x, our dv is e to the x dx, our du is 1 times dx, our v is the antiderivative of e to the x, which is e to the x. So the integral of x e to the x is going to be x times e to the x minus the integral of e to the x dx, which is just going to be x e to the x minus e to the x. And I don't care about the plus c because there's a definite integral over here. It's improper. It's still definite, though. So then using this, we're going to write my limit of my integral as the limit as a approaches negative infinity of my integral, which is x e to the x minus e to the x, evaluated from a to 0. Now we just plug in our limits of integration like one would, kind of pretending like the limit isn't even there. If it helps, and it might help, you might write parentheses around everything, just to kind of remember that, okay, we're dealing with all that before we even think about the limit. Same deal here. So let's see, I'm going to get a limit as a approaches negative infinity of 0 times e to the 0 minus e to the 0 minus a times e to the a minus e to the a. Let's see, that's going to be a 0 minus 1. So I have the limit as a approaches negative infinity of negative 1 minus a times e to the a plus e to the a. And we have a problem here. This a times e to the a is an indeterminate form. We have something, an a, which is going to negative infinity times an e to the a, which is e to the negative infinity, which goes to 0. And a negative infinity times a 0 can be anything. So we're going to have to use L'Hopital's rule. Right, exactly. It's coming back, and it comes back with a vengeance. A lot of these problems have L'Hopital's rule in them, unfortunately. Yeah, you thought you were done with it. You're not. So what I'll point out here is the negative one just hangs. Now here's what I would say. Almost all the time, it is in your interest to re-express things so that your power is positive. Meaning, I don't want e to the a if a is going to negative infinity. I don't want that in the numerator. I want to put it in the denominator as e to the negative a. So I've got the limit as a approaches negative infinity of negative a over e to the negative a plus 1 over e to the negative a. I find that helpful because if a is going to negative infinity, negative a is going to negative infinity, which is infinity. So I have something really, really big in the denominator here. Now, to kind of avoid the issue of this part not requiring L'Hopital's rule, we could get the, oh my gosh, the words. We could write that as one fraction because we already have a common denominator. So we could write this as -1 plus the limit as a goes to negative infinity of negative a plus 1 over e to the negative a. This is an infinity over infinity type. The top is going to infinity plus 1. The bottom is going to e to the infinity. Now, some people, especially in other classes where they don't use L'Hopital's rule as much, sometimes professors are like, you know what? You could probably convince yourself that the denominator is getting bigger way faster than the numerator because the denominator is an exponential function and the numerator is a linear function. And if you've ever graphed those things, you know an exponential function gets bigger so much faster than the linear function. So you can probably convince yourself that, okay, the limit of this is going to be 0 because the denominator gets bigger so much faster than the numerator. I mean, right, plug in -10 for a. The numerator is 11. The denominator is e to the 10th power, which is, I don't know, millions, trillions probably. Anyway, we can also use L'Hopital's rule. Say, cool, that -1 just hangs out in front, and then we have the limit as a goes to negative infinity of -1 plus 0 over negative e to the negative a. And now we have -1 over something getting infinitely large, so that's going to end up being -1 out there plus 0. So we get -1. So this integral converges, and it converges to -1. So the integral from negative infinity to 0 of x e to the x dx converges to -1. And it is reasonable that it's negative because if you graph this thing, x e to the x is negative underneath the x-axis on the left side. So it's totally fine. See how much time we got? Okay. Sure. All right, let's see. What else do I have on the agenda here? Yeah, sure. Yeah. Yeah, let's go that way. What if we had this sort of situation? The integral from negative infinity to infinity of the same thing, x e to the x. So if you have infinity in both, or one negative, one positive, you have to break up the integral. Because the kind of the rule of thumb is you can only deal with one problem at a time. Both of these limits of integration are a problem, so we have to break it up so that we have two integrals, each having one problem. You can break it up anywhere you want. We usually pick 0, although you can pick anything that's in between negative infinity and infinity. So we're going to write this as the integral from negative infinity to 0 plus the integral from 0 to infinity. Okay, so typically, to get convergence, both parts have to converge. To get divergence, if one of the parts diverges, you're done. The whole thing is divergent. So usually you would look at this and try to guess, well, if I was going to look at that thing, which one of those might diverge? I would pick that one first. I would pick the one that might have a chance of diverging. Also, we already did this one, and we know that part converges. So let's do the other one. But I would pick this one first because also I can see that my function on its own, if you look at x times e to the x and you go to the right, it's going to get bigger and bigger and bigger and bigger and bigger. It's probably going to diverge because my function is getting infinitely large. Someone asked, is converges the same as, yeah. So we say an integral converges to the value that it's equal to. So yeah, that means the same thing as being equal to that number. So let's look at this side. The integral from 0 to infinity of x e to the x dx is equal to the limit as b approaches infinity of the integral from 0 to b of x e to the x dx. And we already did the work of integrating x e to the x It was x e to the x minus e to the x. So we have the limit as b goes to infinity of x e to the x minus e to the x from 0 to b, which is equal to the limit as b goes to infinity of b e to the b minus e to the b minus 0 e to the 0 minus e to the 0. Now you might think here, I have another indeterminate form. I don't really, but it kind of looks like I do because I have an infinity minus infinity, which is in the indeterminate form. But you can fix it by factoring out the e to the b and write this as the limit as b goes to infinity of e to the b times b minus 1 plus 1. And now you have e to the b going to infinity and b minus 1 also going to infinity. And infinity times infinity is just big. It's infinity. So this thing definitely diverges to infinity. And since this part diverges, we don't care about this part. This part could converge, this part could diverge. It doesn't matter. This part diverges, the whole thing diverges. So the whole integral diverges. No one's using web work, right? Part like this. Okay. So sometimes for these types of questions, they will ask what the integral diverges to. And if that's the case, then you do have to check the other part. So if this part diverges to infinity and this part's finite, then the whole thing diverges to infinity. Or if this part diverges to infinity and this part diverges to infinity, the whole thing diverges to infinity. But if this part diverges to infinity and the other part diverges to negative infinity plus infinity is wah wah, indeterminate form. You just say it diverges. You don't get to say whether or not it diverges to infinity or negative infinity. And there are plenty of integrals that just diverge and you don't know what they diverge to. Here's a real typical example. The integral from 0 to infinity of sine of x. Just think about the picture of it. Think about what sine's doing and the fact that the area is kind of, I mean, you can think about it like the area is going to be 2, right? The area from 0 to pi for sine is negative cosine of pi minus negative cosine of 0, which is negative 1 plus 1, which is 2. But then negative 2, so 0 total. And then you add 2 more and subtract 2 more, and you just keep going on and on forever. This is going to diverge because when you write this as a limit, it's the limit as b goes to infinity. The integral of sine of x is negative cosine of x. From 0 to b, you get the limit as b goes to infinity of negative cosine of b minus negative cosine of 0, which is plus 1. But the limit as b goes to infinity of negative cosine of b, that limit doesn't exist. If you look at cosine, you're just doing this the whole time, and you don't get close to any one number. But it's not diverging to infinity. It's not diverging to negative infinity. It's just diverging. So this integral diverges. And that's all we can say. It diverges. But yes, sometimes you will be asked if it diverges to infinity or negative infinity. Okay, one more of these type, and then we'll look at the other type. So there's actually one other interesting thing I want to point out. Okay, so without doing any work, at all, I would like to think that all of you could tell me what that integral is equal to. Drum roll, please. The answer is 0, because it's an odd function. Here's some bad news. Not 0. It diverges. Bummer. I know. You can look at an even more basic example. This integral from negative infinity to infinity of x dx. Well, here's the problem. You have to break it up. you have to write it as the integral from negative infinity to 0 of x plus the integral from 0 to infinity of x. And this integral for sure diverges to infinity. This integral for sure diverges to negative infinity. But we do not get to say that those infinities are exactly the same. So this whole thing just diverges. It's kind of disappointing. And I feel like some teachers have actually tried to say that it's equal to 0. That's not true. I don't think your teachers will say that, but in the past, I've seen one or two teachers be like, no, this is equal to 0. Like, not the way it was taught when I learned it anyway. So just be aware that odd functions don't necessarily have an integral that equals 0 if you go from negative infinity to infinity. Some of them do. Some of them totally do. Like, sure, the integral from, oh, where'd you go? I was looking at you. Yeah, this integral from negative infinity to infinity of, let me double check before I get too carried away here. Yeah, of x cubed times e to the negative x to the fourth. This one, if you break it up from negative infinity to 0 and 0 to infinity, each of those integrals will converge, and one of them will converge to, I think, let's see here, 1/4, and one of them will converge to negative 1/4, and when you add it together, you're going to get 0. You should do it on your own. It's going to equal negative 1/4 plus 1/4. So if a function's odd and it converges, then the integral from negative infinity to infinity will converge to 0. But sometimes it doesn't happen, which is always disappointing. Okay, let's look at the other type of improper integral. So one type of improper integral is when one or more of your limits of integration is infinity. Yes.
Like, total answer is 10.
Yes, exactly. Thank you for pointing that out. That's exactly correct. If both parts converge, then your whole integral converges to the sum of those parts. All right, so the other type of improper integral is when your function is undefined somewhere on your interval of integration. For example, the integral from 1 to 9 of the cube root, sorry, of 1 over the cube root of brain. I had a number in my head and now, oh, sure, fine. No, I don't want to do that. That's terrible. Sorry, I thought I had something great. And now I'm lost. Sorry. Let me just fix this. The integral from, yeah, 9 minus x, 1, 8, sure. From 1 to 8. Why is my brain not wanting to make this work? Yeah, sure. That works. 1 over the cube root of, nope, no bueno. Why is it not good? Well, I mean, it's a perfectly fine integral. You know why it's not a good example? Because I tried to be too clever here. Because it's not undefined on my interval. That function is defined everywhere between 1 and 8. So this is not improper. Fine. I'll just stop trying to be so smart and give you a regular example. The integral from 0 to 4 of 1 over the square root of 4 minus x. This is a much more typical first example. Okay, so why is this improper? Because that function is undefined at 4, and 4 is in our interval of integration. So here, we're going to rewrite this as the limit as b approaches 4 of the integral from 0 to 4. I'm going to do myself a favor. I'm going to rewrite my integrand. Instead of 1 over the square root of 4 minus x, I'm going to write it as 4 minus x to the negative 1/2. Oh, except not 0 to 4, 0 to what? Should be 0 to b. Okay, there's one extra thing we need to do here. So when your interval is improper because it's undefined at a point in your interval or at the end of your interval, well, if we're between 0 and 4, what side of 4 are we on? The left or the right? I'm between 0 and 4, so I'm bigger than 4 or less than 4? Less than 4, so I'm on the left side of 4. I'm approaching it from the left. I'm moving right, but I'm approaching 4 from the left. So we do need to actually write this as a one-sided limit. I'm approaching 4 from the left. It's actually super important because this limit doesn't exist on both sides. You can't approach 4 from the right side, because if you're a little bit bigger than 4, the square root of 4 minus x is totally undefined. So we do need to usually we almost always have a one-sided limit for these types of ones. And now we proceed as usual. With the limit as b approaches 4 from the left, we integrate that, we get 4 minus x to the negative 1/2 plus 1 is positive 1/2 divided by 1/2, also divided by a negative 1 because of the minus x there. Yes, I skipped doing the u substitution, right? This is one of those mini u subs where we end up dividing by the coefficient of x. That looks gross. Let's fix it. So limit as b approaches 4 from the left. Dividing by negative 2 is the same as, sorry, dividing by negative 1/2 is the same as multiplying by negative 2. So it's negative 2 times the square root of 4 minus x from 0 to b. And now things are going to work out great. We're going to plug in b first and 0 second. We're going to get negative 2 times the square root of 4 minus b minus negative 2 times the square root of 4 minus 0. As b approaches 4, 4 minus 4 is 0. The square root of 0, we're good to go. That's just 0. Minus minus 2 is plus 2 times the square root of 4, which is going to be plus 2 times 2. So this integral converges to 4. Yeah.
If found in the initial problem were like from 0 to 6 instead of from 0 to 4, would you split it up into 2 integrals?
Yes. Yes, you exactly have to do that. Like, well, I say the problem, so that wouldn't actually work for this problem, because if you're from 0 to 6, the function is undefined from 4 to 6. And so you can't do that. So it has to be a function that's defined like everywhere except for like a couple points. But an example of that, which I was trying to kind of get at before, was something like the following. The integral from, right, that'll work. From 0 to 9 of 1 over the cube root of x minus 8. Because unlike square roots, cube roots are defined if your input is positive or negative. So, but the problem here is that, oh yeah, this function is undefined when x is equal to 8. So we'd have to break this up as the integral from 0 to 8 of x minus 8 to the negative 1/3 plus the integral from 8 to 9 of x minus 8 to the negative 1/3. And then we'd have to do each part separately. So let's go ahead and do this part first. So the integral from 8 to 9 of x minus 8 to the negative 1/3 dx. Now I'll point out, and this is where you have to be really careful. If you looked at this function here, x minus 8 to the negative 1/3, you might be able to erroneously convince yourself that it's not undefined to 8. It is undefined to 8. 8 minus 8 is 0, and 0 to a negative power is like dividing by 0. So just be careful, because sometimes in your solution, you might think you have 0 to a thing that's fine, but I'll remind you, 0 to a negative power is always a problem. It's always undefined. The nice thing here is, though, when we do this, it's going to end up being fine. So we're going to have the limit as a approaches 8 of the integral from a to 9 of x minus 8 to the negative 1/3 power. And since we're between 8 and 9, we're approaching 8 from the right-hand side. Basically, lower limits you always approach from the right, upper limits you always approach from the left. But you can also draw a picture, right? You can literally just be like, okay, cool. Here's 8 and 9. Okay, if I'm coming at 8, I have to come at 8 from the right-hand side. And then we do the integration. We get the limit as a approaches 8 from the right of x minus 8 to the positive 2/3 divided by 2/3 is multiplied by 3/2 from a to 9. And the thing I've noticed over the years is that when you do your integration and you go from having a negative power to a positive power, that usually means things are going to work out fine because your 0 to a negative is now going to be 0 to a positive, which is 0. So usually that's what we're looking for. So we're going to be careful to make sure your A and your 9 look different from each other. You have the limit as A approaches 8 from the right of 3 halves times the 9 minus 8 to the 2/3 minus 3 halves times 9 minus A to the 2/3. But if A goes to 8, sorry, I got that wrong there. I wrote 9 minus A when it should have been A minus 8. Apologies. So when I plug in A going to 8, 8 minus 8 becomes 0 to a positive power is still 0. So we end up getting 3 halves times 1. And then since that converged, we now have to do the other one too. So the other one we're going to try and show a little bit less work for because we've only got a few minutes left. So for this integral from 0 to 8 of x minus 8 to the negative 1/3, it's going to be the limit as b approaches 8 from the left-hand side of the integral from 0 to b of x minus 8 to the negative 1/3. So we're going to get, can I skip this step? No, I shouldn't skip that step. The limit as b approaches 8 from the left of x minus 8 to the positive 2/3 times 3 halves from 0 to b. Be a little bit more careful about plugging things in this time. Plug in b first, I get 3 halves times b minus 8 to the 2/3 minus I plug in 0 seconds. Here's a good example of where plugging in 0 doesn't get you 0. So plugging in b going to 8, 8 minus 8 is going to go to 0 to a positive power. And over here, I get minus 3 halves times negative 8 to the 2/3. Ooh, negative 8 to the 2/3. What's the cube root of negative 8? What's negative 2 squared? It's going to be negative 3 halves times positive 4, which is negative 6. So our final answer is converges to 3 halves plus negative 6, which is negative 9 halves, or negative 4.5. Let me very quickly show you one example of one of these that diverges. It'll be very fast, I promise. So let's say we had something like this. The integral from 1 to 7 of 3 over x minus 7 to the 5th power. So you can probably see that when we integrate this, instead of getting x minus 7 to the negative 5th, we're going to get x minus 7 to the negative 4th because we're going to add 1 divided by the new power. So we're still going to have an x minus 7 in the denominator, essentially, which means plugging in 7 is still going to end up getting us division by 0, which is going to end up giving us divergence. We're still going to show the work very fast, but that's what's going to happen. Limit as b approaches 7 from the left-hand side, integral from 1 to b of 3 times x minus 7 to the negative 5th. Limit as b approaches 7 from the left, 3 times. We integrate that. We get x minus 7 to the negative 4th divided by negative 4. From 1 to b. I don't like having a negative power in this instance because 0 to a negative power is a problem. So I would much rather rewrite this as the limit as b approaches 7 from the left of negative 3/4 times 1 over x minus 7 to the positive 4th from 1 to b. Now I plug in my limits of integration. I get the limit as b approaches 7 from the left of negative 3/4 times 1 over b minus 7 to the 4th minus negative 3/4 times 1 over 1 minus 7 to the 4th. I don't really care about this because right over here, 7 minus 7 is 0. Dividing by 0 is going to give us divergence. So this is going to diverge. Now, I will say what it diverges to. Doesn't matter if this bottom, in this example, doesn't matter if what's inside here is positive or negative because we're being raised to a 4th power. So we have 1 over a very small positive number, which is like a positive infinity, times a negative 3/4. This actually diverges to negative infinity because it's a negative 3/4 times a positive infinity. I don't really care that much, but Tarlac might care. So diverges is enough to say, but diverges to negative infinity. To answer the question from here, someone asked, can I explain why isn't 2 root 4 minus x instead of 2 root or instead of negative 2 root 4 minus x? Basically because of the chain rule. There was a negative x there, so if you differentiate that, you'd have to multiply by -1 the derivative. All right. See y'all on Thursday. I think we started talking about, I don't remember what we started talking about actually.
Thanks for having us.
You're welcome, me too.